welcome to this lecture. Today we are going to talk about the design of a fixed bed type regenerator. So, here we will try to solve a numerical problem. Already we have discussed about the design procedure, what are the type of how we will go about the design of a regenerator, what are the parameters that is to be fixed or finalized from a design problem of a regenerator that we have already discussed in the previous lecture classes. And in this particular lecture, as you can understand that the design of any regenerator is quite similar to the design of a heat exchanger, like where we intend to find out the length or other parameters or the design parameters of the heat exchanger. Similar to that, here we want to decide what are the parameters which will be necessary, like what would be the length of the regenerator, what would be the material or the amount of material to be used particularly for that regenerator, under the condition that the flow rate of the this process is already known, or the temperature of the fluid flowing inside or flowing in the hot stream during the hot period or during the cold period, the temperature of the fluid streams are given. So, first of all, if it is a valve type, as we have said again that this is a valve type matrix and it is made of say copper wire screen. So, this is something new to us. Already we have talked about the packed bed spheres, but this is about the copper wire screen, and this is used as the matrix for the regenerator. And here once we have said about the matrix material, we know its specific heat, particularly at the temperature if it is specified. So, and its thermal conductivity and the density of the material is also given. So, here for this copper wire screen we have a porosity of about 0.7 and its wire screen diameter is 0.5 millimeter. So, it is the oven screen, and this wire diameter is told it is given. So, we have to find out the equivalent diameter and its expression we will I remember in the previous class we have talked about it, and if it is not, we will today we will discuss about that part. That stacked wire screen are contained in two identical tubes. So, its ID is 52.5 millimeter and the working gas is argon. So, it is already, as I have told, that we need to know certain more parameters like the flow rate of the fluid streams and its temperature and pressure. So, that we would be able to find out the fluid properties, and here for this hot stream we know that the temperature of the hot stream is 300 Kelvin. It is entering at a pressure of 608 kilopascal and its flow rate is 20 gram per second, whereas the cold stream is entering at a temperature of 100 Kelvin at a reduced pressure of 304 kilopascal, but its flow rate is not equal to the hot flow rate, and its flow rate is reduced slightly by 19 it is 19 gram per second. The switching frequency of the regenerator is 3 cycles per minute. So, that means in every after 3 cycles per minute the hot fluid and the cold fluid stream will change, and for this particular problem we have already specified the heat transfer coefficient. Otherwise, this is generally it is not known, and we are supposed to find out once we have told about the wire screen and its flow rates are known. So, the heat transfer coefficient and the pressure drop or the friction factors can be obtained from the correlations corresponding to the copper screen. And but however, for this the problem we have already evaluated it, and it is the hot and the cold fluid heat transfer coefficients are given as HH and HC, and what we are supposed to find out is the length and the mass of the copper screen required to achieve an effectiveness, regenerator effectiveness of 0.98. So, if we have to achieve 98% efficient regenerator effectiveness, what would be the mass of the copper screen to be used, and what would be the mass or what would be the length of the regenerator that we have to specify or we have to calculate. So, these are the parameters that has been given, and the procedure that we have to follow, we will first look into that, and then we will go about the solution of this problem. So, first of all, we will try to find out what is the average fluid temperature to find out the specific heat or the fluid properties. Then we try to calculate, since we know the mass flow rate of the fluid hot fluid stream and the cold fluid stream. So, we would be able to find out the hot fluid capacity and the cold fluid capacity, and from there we would be able to calculate the capacity ratio CR, because we know that depending on the CR value, whether it is CR equals to 1 or not, then our calculation will change. So, once we know the CR value, and we will be, if it is not CR equals to 1, then we will go for this calculation of this x parameter, and given by this relation ln into 1 minus epsilon CR divided by 1 minus epsilon. So, from there we would go to the calculation of epsilon 1, and this epsilon 1 is again this correlation is given already, we have talked about it. So, we will try to find out this epsilon 1. So, now we have an effectiveness corresponding to this CR value based on that x, and this epsilon is what we are looking for. Epsilon is 0.98, we are looking for an effectiveness of 98%. So, from there we will be able to calculate x, and we will be able to find out an equivalent epsilon 1. So, that is equals to given by this correlation. So, once we know that, we will try to now find out the CM, the matrix capacity rate ratio. So, this but please note that we have for this parameter we need to know the mass of the regenerator and the specific heat of the regenerator, but unfortunately this is one of the parameter, that is what we are trying to find out. So, we have no idea about this CM. So, if we do not know, what we have to do is that we do not know about it. So, we will assume some equivalent value of this one, and from there we will already we have the value of this epsilon, because we have already epsilon 1 we have calculated based on this parameter x, we have calculated epsilon 1, and we have assumed some value of CME. So, once we have that CME and equivalent matrix capacity rate ratio, and then we have the value of epsilon. So, we would be able to find out the equivalent NTU. So, like if we have find some value of this epsilon and corresponding to say 0.98 or something like 0.968, for example, if we have obtained say 0.968 and we have assumed say value of CME equals to 1.5. So, the corresponding NTU is 60. So, that is what is depending on the value of this epsilon 1 that has been obtained and the approximation or the assumption of CM, we would be able to get some equivalent NTU. So, once we know that equivalent NTU value, we would be able to calculate the NTU based on this relation. So, once we know that NTU value, then we have we can put it in terms of NTU equals to UA by C mean, and you note that this C mean part is already known to us, because already we have calculated CH and CC. So, out of these two we would be able to find out or distinguish which one is the C mean. So, once we know the C mean, this NTU part is already known, the C mean part is known, we would be able to calculate the UA. Now, you note that this UA is basically nothing but 1 by H and AH plus 1 by HC AC whole to the power minus 1. Here most of the cases you will find that the regenerator are fixed bed regenerators. In case of fixed bed regenerator, this AH is equals to AC, and we can take out it from this outside this one, and also we need to have an estimate of this HC and AH, HH and HC, the heat transfer coefficient for the hot fluid stream and the cold fluid condition. And accordingly, as you can understand that we have already have an estimate of this UA. Since we know this UA, and we have already knowledge about the HC and HH and HC, we have the we can calculate the heat transfer surface area corresponding to the hot fluid or the cold fluid stream. So, once we know this surface area, we know what is the ratio of heat transfer area per length, and or generally it is in terms of the AW by V0 corresponding to the packed bed sphere or corresponding to the wet screen mesh oven screen. So, from there we would be able to find out this AW by V0 is already known in terms of its porosity and etc. And then we would be able to correlate it with this V0 will be correlated with that length, and from there we would be able to calculate the length of the regenerator. Particularly for this problem, we know that this A0 by L or AW by L is given by, for a wet screen type process, AW by L is equals to 4 times 1 minus EV multiplied by A frontal area divided by dW. What is this dW? dW is the diameter of the wet screen. EV is the porosity or the void inside this bed, and this A frontal is the frontal area of that bed. So, accordingly, as we have obtained the AW and we know the frontal area, we know the wet screen diameter, the porosity. So, we would be able to find out the length of the regenerator. And now, once we know the regenerator length, we would be able to find out the MS, the amount of the element or say the wet screen, the copper wet screen that will be necessary. So, this is given by 1 minus EV into rho S into V0. So, this is EV is known, rho S is already been given, and V0 is the volume of the regenerator, and so accordingly we would be able to calculate the mass of the copper screen that would be necessary. But please mind that it was based on an assumption that we have assumed some value of CME or the matrix capacity rate ratio, and because we did not have an idea about this MS. So, we have done all this calculation based on some value of the MS, and now we are getting some value of this MS at the end. Now, obviously, we can understand that this depending on our initial guess, this may not be the same. We have based on this MS, we will now be able to calculate a new value of the Cm, and that value of the Cm will give us a new value of the Cme, and from there again we will get NTU effective, and from there we have to calculate the NTU. From that NTU we will be able to calculate that UA by C mean, and the procedure will be repeated. So, that means here this process becomes an iterative process. So, based on our initial assumption of that Cm, our next calculation or the number of iterations that are to be done will depend. So, if we make a good estimation of that Cm, the number of iterations will be less. Otherwise, if we are making a bad estimate of this regenerator capacity Cm, we will land up with a different mass, and we have to do number of iterations to get the actual value. So, as you can understand, this is the procedure for doing the calculation or the regenerator design. So, now we will go to the slide. We will try to calculate for this particular problem which we have defined in this case. So, here we have been told that we are going to use a valve screen, a valve type regenerator, and this regenerator is made of this copper wire screen. Its porosity is given, and the other parameters like say rho W, that is the density is coming to be 8900 kg per meter cube. This is we are talking about the copper, and then specific heat Cw, it is also 0.350, and it is kilojoule per kg Kelvin. This is the specific heat, and then we have the thermal conductivity Kw or Ks, this is equals to 300 watt per meter Kelvin. So, these are the values we have for the material, and once we know this material, we have to now look for, as we have said, that we need to look for, this is for the material part or this is for the copper, and we need to look for the gas part. The gas is argon, and this gas is, we have already said that this gas is argon, and it is entering at some temperature and pressure, and it is moving out with at some different temperature and pressure. So, its inlet temperature was 300 for the hot and 200 for the cold stream. So, we will take it, sorry, the 100 as the for the cold one. So, it is at an average temperature of 200 Kelvin. We will try to estimate its property, and the Cp corresponding to this value is 0.524 kilojoule per kg Kelvin. So, that is what is the Cp value of this argon gas. So, this gaseous argon Cp, once we know, we would be able to calculate the heat capacity of the hot fluid and that of the cold fluid. So, now we see the Ch equals to mHch, and that will come out to be 0.02 multiplied by 524, and this comes out to be 10.48 watt per Kelvin. Similarly, the Cc is mCcc, and the mass flow rate of this one is slightly less, as we have seen. This is 0.019 multiplied by 524, and this many watt per Kelvin, and this comes out to be 18.87 watt per Kelvin. So, as you can understand that this is the sorry, I am sorry, this is 9.956 watt per Kelvin. So, it is the C mean and this is the C max. So, this value is the C max value and this value is the C mean value. So, we have the C mean and C max, and then we would be able to calculate the CR. So, this is C mean by C max, and from there we would be able to find out that this is nothing but 0.950. So, we have an idea about CR and CR not equals to 1. So, already we have an idea about the CR. So, we have the idea of CHCC, and now we would be able to calculate the X factor, that parameter, and that will come out to be we have already told about the expression of this one. So, 1 minus 0.95 multiplied by this is CR multiplied by the epsilon 0.98 divided by 1 minus 1.98, that is the effectiveness. So, this X comes out to be 1.238. 1.238 is the value of this X. So, corresponding to that value, if we put it in that value of the epsilon, we get this epsilon 1 to be 0.9602. So, this is the value of epsilon 1, and at this point what we need to do is that we need to calculate the matrix capacity rate ratio, and which is not known Cm, as we have said that it is, we have no idea about the mass of the regenerator material that will be necessary. So, we will make an assumption about this Cm equivalent CME, and that has been chosen as 3 for this particular problem. So, once we know that Cm equals to 3 and we have an idea about this regenerator effectiveness. So, 0.960 is the regenerator effectiveness, and the equivalent this capacity ratio is 3. So, corresponding to those two values, we will go back to that NTU and CME relation, particularly for the epsilon. And so, we have this value, we have this value, we will go for this value. So, accordingly, we will find that NTU, if you use that chart, you will find that this comes out to be 29.6. So, once this is known as 29.6, we would be able to calculate the value of the NTU. So, this NTU comes NTU and NTU equivalent, they are related by this relation NTU effective divided by 2 CR. So, we have this NTU coming to be 30. So, 30 or 30.4, actually this is 30.4, and so this is the NTU value based on our assumption of CME equals to 3. So, we are getting a value of NTU equals to 30.4. So, once we know the NTU, we would be able to calculate the it is just nothing but UA by C mean. We have the idea about C mean, and this is UA would become 1 by H C A C, we are calling it say W plus 1 by H H A W, and this whole to the power minus 1. So, already this is known. So, UA by C mean is already known, this part is known, this is this will come out to be say A W divided by 1 by H C plus 1 by H H whole to the power minus 1, and if we put this value or divide this value by C mean, then it comes to be UA by C mean, that is equals to the NTU, that is equals to 30.4 multiplied by C mean value was C mean value was 9.956. So, that is equals to AW into 1 by HC plus 1 by HH whole to the power minus 1. So, here if you look at, you will find that already we have talked about this HH and HC. So, we can find out the AW, and from there we would be able to calculate this AW to be 1.732 meter square. So, this is what is the area needed for this particular regenerator to achieve 98% porosity, but please mind that we have made an assumption that the CME equivalent is 3. So, now once we know the area, we would be able to, as we have said, that we will be able to calculate the length. So, AW by L is 4 into 1 minus EV and multiplied by A frontal area divided by dW is the wet diameter, and from there if we put all these values, EV is 0.7, then we have the frontal area that also is about 0.002165, and the wet screen diameter, this is equals to 0.50 multiplied by minus 10 to the minus 3, and from there we get AW by L is equals to 5.195 meter square per meter. So, already we have the value of AW, we would be able to calculate the length and it will come out to be 0.333 meter. So, this is the length of the regenerator. So, now we have the mass, that is equals to 1 minus EV multiplied by rho s into V 0, and then if we put these values, that comes out to be 1.927 kg of copper screen. Now this is we have an idea about the MS. So, once we have the idea about the MS, we can now you can see that we would be able to calculate the CM, because we know the CM equals to MSCS divided by that P 0 and that other parameters. So, once we have that one, we would be able to calculate the matrix capacity rate ratio, and from there we get the second estimate, this will come out to be 3.387. So, we have quite a good estimate of this CM, and accordingly you will find that CME is coming to be 0.3, and from there you will be able to calculate the mass, and so there you will have this NTU equivalent to be 29.3, and finally this length will converge to nearly about 0.33 meter or 330 mm. So, here that will correspond to a mass of about 1. The total mass will come out to be about 1.906 kg of copper screen. So, this is in a nutshell about the design of this regenerator, and but please mind that in many of the cases we will not have this idea about the this heat transfer coefficient, and we have to depend on the correlation, existing correlations, or we have to depend on the experimental value of the heat transfer coefficient to design this kind of regenerators. Thank you for your attention.